All right, guys, welcome back. And so now we're going to do 3.1, and we're going to look at 16, 24, 35, and 43. So the first thing I want to do is I just want to take a minute to say you need to kind of take a step back and remember that we have lots of reasons we've been using limits. Okay? What we're talking about now when we talk about this new concept of derivatives is we're talking about taking the limit of this thing. And we're talking about when we take the limit of this, we get what we call a derivative. And a derivative is just consider simple x squared when x is greater than 0. As you can see, the slope here is kind of low, the slope here is really steep, and it's a curve, so the slope is changing everywhere, unlike a linear function where the slope is the same everywhere, like a y equals mx plus b. So the question for early physicists, because x squared, of course, was useful in measuring objects under the force of gravity, is you would say, well, what's the slope at any instant, and what's the rate of change? Which would then be how fast it's going at that particular curve, if it was the derivative of the acceleration function. So that could be very useful information. So let's consider a simple scenario here, and I'll zoom in even more to this little graph here. Okay, and in our simple scenario here, we have a point x on y equals x squared, and it has a y point f of x. Then some distance forward h, which would be x plus h, would be this point here, and that point would be putting x plus h into f, which would be f of x plus h. So we have 2 points, x, f of x plus h, and f of x plus h, and there are 2 points on here. When I connect those 2 points and I cross through the function, I get what's called the secant. But what we want to do is take the limit of this thing. The limit of this is the second y point, the first y point, second x point, first x point, right? Second and second, first and first. And so really this is just the slope equation. Without the limit, this is just the slope equation. What we want to do though is take the limit as that increment of h collapses to 0, so that instead of getting the slope of the secant line here, we get the slope of this imaginary tangent line, or what's actually the slope like right at that instant there, okay? Like you obviously can't draw it because you're drawing more than a point. But there's a rate of change that's happening right there that's different than the rate of change here and here and here and so on. And what is that rate of change? Well, that rate of change is when you actually take the limit of the slope equation, which is this guy here. And the slope equation, if you plot a line through it, gives you a secant or cutting line. And you can also write the slope equation this way. This way is simply more useful for evaluating the limit because everything's a function of x explicitly. And then you can let h approach 0, and algebraically that can let the h fall out. So the limit of the secant is the slope of the tangent, or of f of x right at that value, the slope of the f of x function, right at that x value a, okay? Or a tangent that we may want to draw to it for either approximating values after or before or other things. Tangents can be useful in approximating values close to the point x equals a. So we want to keep our eye on what tangents are. And in fact, we're going to see them in our first problem 16. So just wanted to take a step back. You take that step back with me. We're not talking about limit as x approaches a. We're not talking about horizontal asymptote, x approaches infinity, okay, which can sometimes result in a horizontal asymptote. We're not talking about x converging on a value a from one side. This is a two-sided limit, and there can be approaching 0 from the left and approaching 0 from the right. But we're not talking about the simple case of that where it's of a function. We're talking about a two-sided limit where a particular value in this function approaches 0, but this thing here means something. We're taking the limit of slope. And when you take the limit of slope, you get what we call a derivative, which gives us a way of knowing the slope at any instant for any curve or function f of x. And so that's big news. Before the calculus, before it was formalized by Newton and Leibniz and the thinkers shortly before them, there was no way of doing that. And knowing that and knowing how what changes, that gave Newton a rich tool to be able to describe the cosmos and the Principia. So you should know what we're doing before we just dive into these problems. That's my mini lecture on what we're doing, where we're headed, which type of limit we're leveraging. Now that you're a little bit more familiar with limits, you're like, oh yeah, it's like a two-sided limit at a point, but it's of a thing that means something. So we're taking the limit of a concept, and that makes a new concept. And we know visually what it means because we can just see that as we make these h values smaller and smaller and smaller, that secant just collapses here to be what's at that instant. It's brilliant. And that is the definition right here of a derivative, and it is the first thing that we do. It's the first branch of Calculus 1, derivative calculus. And then the second branch will be how do we get the area under a changing curve, and that will be integral calculus. Okay, so now that we have that as a context, let's go ahead and dive into 16. So if you're looking just for the problems, that'll be up there like I promised, and there it is. And you can hear me shuffling because I deliberately want to stall here so that it stays up there for a bit for you guys to find. I'm now going to encourage you to write out 16, give 16 a try on your own, see how far you can get, and then come back and join me here. All right, so I had to take a little break there, so sorry for the awkward pause in the video, but whatever I didn't say, whatever doesn't flow, I apologize, but 16, I think I was giving you the overview of what we were doing with limits now, and that we were using limits to make tangents, broadly speaking. I don't remember exactly where I was in talking. And so knowing that we're doing that now, they're giving you a common function, and they're telling you to find the slope at this particular point, because now we know how to do that. And they're telling you to then determine the equation of the tangent line at that point, and then they're telling you to plot the function with the tangent. So the first thing that I want to focus on is C. If we're going to need to plot this, then we need to know how to plot this graph. And in order to plot this, we need to be able to complete the square of quadratic equations. And we need to be able to do that easily without any problems in pre-calculus. So we're going to do a dummy 0. Okay, so I put a dummy 0 here, and I'm going to set it equal to all this stuff. I'm now going to divide my A out from every term over here, and of course what I do to one side, I do to the other. Okay, if you want to think of it as if you don't want to use a dummy 0, because you'll be like, hey, it equals 0, think of it as actually, technically speaking, f of x divided by -3, and so it's always that, and so at the very end you are going to have to bring back in the -3. I just do a dummy 0 to make it a little easier for students algorithmically. You do whatever convention you want, just make sure you know how to complete the square. So now we have this and this. So I'm now going to add the 1/3 to the other side, just normal completing the square mechanics at this point. Make a note, and I usually make a big arrow, okay, and put something like bring back A. Leave yourself a note or you'll forget to do it when you're doing your work. And then here we take our B, we split it in half, we square that, and then we add it to both sides. And if you don't know that doesn't look familiar to you, then you need to brush up on completing the square. So 5/3 divided by 2 is equal to 5/3 times 1/2, which is 5/6. And then we square that and we get 25/36. And we add that to both sides. So 25/36 here plus 1/3 equals x squared plus 5/3 x plus 25/36. I'm going to take that and just drop it down here into this section. Okay, so let's first deal with this side, because completing the square we now have a perfect square here. And so this side's going to be x plus 5/6. Again, 5/6 plus 5/6 will be 10/6, which reduces to 5/3. So if you add your inners and outers, you see that works. And 5/6 times 5/6, of course, is going to be 25/36. Now we're going to do some scratch work here for this one. We're going to change 1/3 to a fraction over 36. So that'll be 12/36, and 12/36 plus 25/36 is 37/36. And so now we have that. And what we're going to do now is we're going to minus the 37, 36 over to the other side, and we're going to bring our a back in. And let me just make sure, hold on. Was this negative 1/3 over here? No, it was negative 1/3 here, divided by negative 3. So it's negative here. I'm just checking my work with you guys here. So it's negative 1/3 here, which means when I bring it to the other side, it's positive. So it's definitely 37, 36, positive here. I bring it to the other side, it's negative. Okay, I'm just checking my signs. And now we can replace the dummy variable with an f of x, so long as we remember to multiply back in our negative 3 to get it out of root form and put it back into the actual form that it is. So if we multiply everything here by that same negative 3 that we took out to begin with, we're now going to get negative 3 times the quantity of x and 5/6 squared. And the negative times negative is positive, and 3 over 36 is 1/12, and we get 37/12. So now that we have this, we're going to write that again, and we have an idea of what to sketch as we look forward to step C. For me, I want to get the heavy lifting out of the way, and if I know I'm going to have to sketch something like I've told you guys and like you've told me you appreciate, you want to know how to be able to graph that by hand and have a sense of what's going on. So I now know that at negative 5/6, will give me a nice big scale factor. So right about there, I have my vertex. And at negative 5/6, that'll be negative 5/6 plus 5/6, which is 0. So this all drops out. So this is often called HK form because it gives us the points of the vertex, which are going to be at negative 5/6 and then 37/12. 37/12, 3 times 12 would be 36. So that's 3 and 1/12. So it's just over 3. So right about there at 3 and 1/12 is where the vertex is going to be. And then we're going to have some x-intercepts, but our point is that our, and at x equals 0, you could plug in x equals 0 here and see it exactly where you're going to hit it. But our graph should be looking like that. Again, my tilt isn't that good, but that should be more or less accurate. Let me check out with technology, make sure I didn't make any mistakes. Okay, so just like I've told you guys, I did all of that heavy lifting, and then I went ahead and plotted it in Wolfram Alpha to get a sense of what it looked like, and I made a quick adjustment. I was like, oh, it doesn't go that wide. It's negative 3, which is going to make it squish together. So it's going to actually hit here relatively quickly, and it's going to be underneath the x-axis when you get to x equals 1 here, which is the point that they asked us to evaluate. If we come back over here, we see they asked us to evaluate 1, negative 7. That's also what gave it away. So in kind of confirming with technology and checking that, all I did is I made a small adjustment on my scale factor, but I have a really good sense of what's going on now. The next thing I'm going to do is go through my list of what we had to do. So bringing that back up, we're going to need to find the slope at that point, and then we're going to determine the equation line of the tangent line at that point, and then C, plot the function with the tangent. So I can now that I know that this is what's going on, I can easily fix that up. You're going to have to do some scratch work and some redoing of work, so to speak. So good to know. We know how to graph that function now without having to rely on technology. Now let's go back, and in order to find the slope of the function, we're going to need to use, I believe that they haven't shared the formal derivative at this point. I'm going to double check, but they want you to use the limit of the difference quotient method still. I'm going to double check that right now. You guys should as well, but I believe you're going to use our good old friend, this guy, okay, to find the slope at that point. What you're going to learn later is instead of using this every time, you're going to learn how to do this thing on all of the parent functions. All of the parent functions will have this guy done to them, and so then there's going to be specific rules for like x to the squared, for your trig functions, for your natural log functions. They're all going to have a unique algorithm. But every problem could theoretically be done with this. And I believe that at this stage for you, they're still wanting you to do that because it's like the early chapter on derivatives. But I'm going to confirm, you confirm too. I believe you're going to use this. And remember, what is the limit of the slope? The limit of the slope is the derivative, and the derivative is the slope at the instant of a curve that has changing slopes all along it. So that'll give you what they're asking for there, which is the slope at the point x equals 1. So pause the video now, you try to plug all the stuff you have into that and evaluate that limit. And I read the instructions more closely and I was directed to this page, so I'm so sorry about that if you paused the video there and actually tried it with that form. It's longer, it does work. If you did that, bear in mind, don't worry, this would work. So if you just did all that work, it does work. But they gave you an alternate form to that guy. And the alternate form, they showed you that the secant could also be represented, like if we put an a here and an x here, it can be represented by f of x minus f of a. So I went ahead and sketched that out for you too. And so that's the same thing that I showed you earlier, except we're just doing it a different way. We're saying if we start at some point a, and we go to some distance x, then the bottom part of that slope, my rise over my run, here's rise, here's run. So the slope between those 2 points will be given by rise over run. This is the run, or the denominator, and the rise is going to be the difference in height between f of x and the first point, which is a and f of a. So f of x minus f of a. And then the limit as x becomes a is what we want. So x is a distinct distance from a, and if we decrease it in stepwise, it can get closer and closer to when we're a, and that would mean the limit as x approaches a would be that distance, would be that decreasing or converging down to this distance. And as we converge down, those triangles get smaller and smaller to where the next triangle would be right here, and it would be the slope at that exact point. And so again, this one would be the secant, this one would be the tangent. So this is just called the alternate form. So sorry about that. And yes, the alternate form is going to be easier for some proofs, just for doing some problems. It'll be easier for making proofs of some of these functions and general rules for some of these functions, so we don't have to use these two to solve every problem. So repause the video if you did already. Again, you don't have to do it both ways. If you did this way and actually got the correct answer, I believe it's 11 or something, you're totally fine. You can stop. Both forms will actually work. This one's just longer for this particular problem. This one's easier for this particular problem. And it's my boneheaded, self here that messed this up for us, because they said, I believe right in the instructions, and I didn't listen to them, to leverage that definition right here. So they said use definition, page 133. So they want you to use the alternate definition. So pause the video and write out that alternate definition. I'm going to do the same thing. My mistake there. But we didn't lose any time, and both of these are valuable. So keep that in mind. And voila, when we do this form, and hopefully you pause the video and try to get as far as you could, here's what we get. Now I know you're seeing a hot mess here, so I'm going to pardon me, sorry for coughing on camera, but I'm gonna narrow in your attention to specific parts here. I'm gonna do that this old school method, but I'm gonna make sure you're only looking at what you need to look at. So we're gonna take this definition and we're gonna use it for the function we have. And what function did we have? We had negative 3x squared minus 5x plus 1. Okay, now we completed the square to be able to plot it by hand, but for this form, it's way harder, if not difficult, to put it in completed square form here. So we're going to use this form because it's nice and easy. Expanded form is what we would have to do anyways. Like if we put it in completed square form here, in order to solve it, we'd have to re-expand it, which is this. So just put it in expanded form here, EF. So complete the square form helps with the graph. That's what HK form is for. And then expanded form will help with the algebra of this equation. So our f of x part is all of this. Okay, there's our f of x part. Our minus f of a is, in this case, remember they gave us the point. They said 0.1, negative 7. So if we plug in 1 for a here for x and do f of 1, then we plug in 1 to this, and we're going to get our output here. And when you plug in 1, okay, we're going to briefly come down to here. Instead, do a little paper shovel here. When you plug in 1, you get -7. So now we come back over here, and we have, now on the numerator, you have minus -7. And minus -7 is plus 8. So we have plus 8 down here. Okay, so now, let me shuffle my papers. So now you should see that we have the x minus 1 drops down, and the -3x squared minus 5x, okay? And then the plus 1 minus f of 1, which is -7, is positive 8 here. Also, note that x minus a is x, which in this case they told us 1 -7, so it's simply 1. So x minus 1. So now we're all the way down at this equation here. And in order to evaluate this, we have to do some different things. So to evaluate this, we first need to factor the top. So I pulled out the -1 and made it 3x squared plus 5x minus 8. It's the first thing I did. I then multiplied a times c, which is 24. I get 1 and 24, 3 and 8, 4 and 6. With the -1 factored out, I need to get a positive 5, which is going to be -3 and positive 8. So you do x minus 3, and you do x plus 8 here. And that's what we start with. What we're going to do now is we're going to divide the a out, which is the 3. Okay, so we're going to do x with 3 over 3, turning this to x minus 1. And again, some of you might factor differently, that's fine, but we saw a lot of those problems, so take this method, use it if you want. If it doesn't help you, what you're doing works, that's fine. Now I have the x plus 8 here, but I have an a term, so I have to divide out the 3. So, and then this is the root. This is in root form, which 2 of you left it in root form. It's true that -3/8 is where the root is, or the 0 of this particular linear factor. But we need to put it in factored form. So I'm going to multiply the a back in, 3x plus 8. Again, this isn't a class on how to factor. If you don't know how to factor, you do whatever you need to do to learn how to factor. I'm teaching you how to factor here in case you never had an Algebra 1 teacher that really taught you a firm method. This method works every time. So now that we have that all factored, we have -1 times x minus 1. I factored out the negative here in order to make it easier to factor, and I just dropped down the negative down there that I pulled out. I rewrote this as a different form up there, pulled it out, and now I have this. Those x minus 1's cancel out, and I have -1 times 3x plus 8. So that limit is now in a form that we can evaluate. So we have the limit as x approaches 1. Again, a is 1 in this case from the point 1, -7 that they gave us. And if we plug in 1 here, we get -11. So I believe we now know what this graph looks like, and we have a really good sense, and we now know what the slope is, and the answer to question A. So I'm just kind of zooming out here and regrouping ourselves. Let's look over at the book here and see how they wanted us to answer this in what order. Okay, so let's write things nicely again. I'll go ahead and pull up a fresh piece of paper here. And so we're for f of x, -3x squared minus 5x plus 1, evaluated at the point 1, -7. We know to find, what did they say, the slope of the line? Okay, so we can answer that now. We could say part A, the slope of the tangent at x equals a is, what did we say, -11? Yeah, -11, okay? And then you would have your work, and you would say, in your case, as students, I've stepped you through how to do it. You'd say because, and then you would show like all your algebra, and it would be all this algebra. You'd leverage the second or alternate form of the definition of a derivative, and you'd go through all the steps that I went through here to get down to here. And of course, when you write that pretty and you're not explaining it and reminding people how to factor and everything, it's a little bit smoother. And you just write that here, okay? And then we'd skip down to part B. Let's take a look at part B. I think we can do part B pretty easily here. So determine an equation of the tangent line at P. So yeah, that should be pretty routine. You might remember that I said your best friend here is point slope form, which is this guy. And again, pause the video. If you pause the video and try to get this on your own, and hopefully you're back now, and let's see what you got. So it's going to be y minus -7 equals, and our slope at that point is -11, and then it's x minus 1. And now we're going to just rewrite this. That's going to be +7, so it'll come over here as -7. That'll be -11x. That'll be +11 minus 7. So a final simplification of y equals -11x plus 4. So, and then we know what part C is, right? Part C is to plot f of x and the tangent line, which we just got here together. And for that, what we're going to do is leverage technology. So let's do that now. And again, I'll remind you, we're only leveraging technology here for the final answer because I already showed you how to not be reliant on it. Remember, we took the -3x squared minus 5, it looks like a 3 there, but it's not. 3x squared, sorry, just like a 2 that had a bottom loop that got carried away. We already took this guy and I showed you how you could have plotted it without relying on technology. And then we can see that the tangent line is -11x, which is really steep, plus 4. And that makes perfect sense because 4 would be like this line here. So our tangent line would be like, you know, super steep here. And it's like, you know, the parabola is like coming right there through it. It's really hard to get the scale factor perfect, so we could adjust our line a little bit, but you can get the general idea. That's a -11x plus y-intercept 4 line coming through there. So hopefully this is really rich, really helps you seeing how to graph these by hand. And then you can go ahead and make sure that you can complete the square. Obviously make sure that you know how to do your Algebra 1 equations from many years before, plot B, and then find the next point using rise over run. And you can sketch this out, hopefully having used a combination of hopefully having done it the way I did, which is to first complete the square and plot it by hand, and then verify your results afterwards. Let's now just verify our results. So -3x squared. And remember, there's no way to plot it by hand in this form. This form you'd require using a table of values, which is not curve sketching. That's doing iterations, and iterations is not what we're learning right now. And this would just be 11x, sorry, -11x plus 4. And there you go. You can see that it, you know, it follows along that line. It's a really good approximation for quite a bit of time in between 0 to 2. So from like 1/5 or so, you know, anywhere in here even, it's still a pretty good approximation. So that tangent line can be used to approximate it can be used for two things. One, the slope of it happens to be the instantaneous rate of change here, but it also gives you a way of approximating what these values are with a pretty good degree of precision. So, and that's just pretty interesting and something cool to keep in mind. Okay, so I think we're done now with number 16. And so let me just pull these notes back up. So again, you would just include your plot here. You know, something like this, you know, make sure to include your x and y axis, right? And all that good stuff, your vertex and x, a y, maybe that this is 0.4, that's 0, 4, or at a y height of 4. You know, write in what this equation is. This is y equals -11x plus 4. Write in what this equation is, y equals -3x squared minus 5x plus 1, and so on. Make sure you notate everything and you get it nicely labeled and so on. and then you're done with part C. So there's part A and part B and part C. And so just to recap, we had to, for part A, we had to do all of that fun completing the square, which we did to get this guy. And, excuse me, we didn't need to strictly do that for part A. We needed to do that to be able to get to where we could plot it on our own, so I did that first. So forgive me, I did the heavy lifting for part C first to get you guys while you were strong in the beginning of the video, because a lot of students forget or come in with shaky completing the square skills. Completing the square is so that when you look at this function here, you're not like, I don't know what it looks like, I don't know what to do. Or you don't have to do negative, you could also do negative b over 2a, comma f of negative b over 2a. That's a lot of points to plug in. Just get good at completing the square and you know right where the vertex is just from doing that. So if you're going to take the time to do all this, complete the square, because it tells you so much more. It tells you that it's facing down. It's telling you that it's shifted this way. It tells you that it's shifted this many units up from where it would normally be. So you know its shift, you know its transformation. Once I did that, I plotted it, I had an idea of what we were doing. We then came over here, and for a brief minute, I advised you to use the limit of this difference quotient to find the slope. But then I looked more carefully. The book wanted you to use the alternate form. I used the alternate form. I did all this business. I got that our slope is equal to negative 11. Again, why does taking the limit of the slope equation give us the slope at that instant? Because you're taking the limit of a linear slope, which is that whole line, and then you're collapsing that x into a so that it's no longer, so that x and a are the same thing, so that it is actually at an instant. But by massaging the algebra, you don't have to substitute in 1 when it makes the denominator 0. You sub it in over here once massaged, and it tells you what the limit is by the logic of limits without breaking the rules of math by dividing by 0, which is kind of creepy. And it's a problem that some of the early people of calculus had with the calculus, because they were like, how can you do that? But we do that and we see that we're good to go, and that actually gives you the slope of the tangent line right at that point. And this is, of course, the generic graph. We know that we're dealing with a tangent like this. But the same logic of having x converge on a and doing the limit of that slope equation to get the instantaneous slope on the curve itself instead of the cutting line, instead of the secant, is brilliant. And then finally, once we do that, we use point slope form to get the tangent line. So this steps you through how to do one of the big kid derivative problems in this section. So you hopefully are feeling a lot better. What we're going to do next is 24. Stalling here a little bit. Keep that up, make sure that you guys can see it. Took a little while to get there, but this is the start of a new heavy-duty section for you guys. So definitely want to make sure that you get a lot of information there on 3.1 where you don't just dive into doing problems. So let's go ahead and look together at what 24 is, and let's write it out. And then we'll do what we've been doing, which is I'll pause the video, you pause the video. And of course, my pauses are different than your pauses, LOL. But let's write that out together. So 24 is f of x equals 8 minus 2x squared. Oh, wait, I'm sorry. I don't want to do 24 because 24 is going to be good practice for you. Because everything that I just showed you in 16, I lied to you, we're not doing 24, we're doing 35. Everything I just showed you in 16 is the same stuff that you do in 24, okay? What the easier part is that they just skipped C. You don't need to plot them, okay? But if you look at 24, 24 is a pretty simple function. It's negative 2x squared plus 8. So if we wanted to, so I'll give you a quick hint on 24. Let's do that. So if I plug in 0, I'm at 8. 8, just so you can visualize it, okay? I know they said you didn't have to plot it, but so I'm not sure it's much of a hint for solving the problem, right? So, and then they're telling you to evaluate it at point 0. So they want your slope at point 0, okay? And I think you can guess what it is, but you're going to have to do all the algebra that I just showed you how to do. You're going to use this guy. The limit as x approaches a of f of x minus f of a over x minus a to evaluate what the slope is right there. And I think you can guess what it is from looking at my sketch and reasoning through what this plot looks like. So I think they're deliberately leaving off c here to see if you're kind of savvy enough to plot it anyways, so that you can kind of make a prediction on what that slope might be. And then you still need to determine an equation. Remember, a line that looks like that with the slope that I think you know what I'm referring to, that still has an equation. There's a y equals stuff line that you can get an equation for that. All right, so what we're actually doing is 35. And I will restall and leave that up now to do 35 instead. Apologies. Stalling, 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 and done stalling. All right, so write out 35, get as far as you can on your own, and then when I magically come back, which you won't notice that I was even gone, then we will do it together. All right, so you should have written this out, and so we're being asked to find that same good old stuff that I warned you that we would be being asked to find, which is the tangent lines, right? I warned you, you're going to do lots of tangent lines now. The only thing they gave you is they gave you new notation. So there's some point x of a, and then just bear in mind that f of x is the original function, but also bear in mind that we're now going to use a prime. F prime of x means the function that will give you the derivative, the value of the slope at any point. There's also going to be a function for that, and there's going to be rules that you learn that I talked about earlier. Again, when we leverage this guy here, okay, and we leverage him instead for not just a particular problem, but I leverage it for just like the most fundamental of all, like the parent functions. So I leverage it for x squared, and I put that in symbolic form here, and I leverage it for natural log of x, and so on. There'll be specific rules that we can use, and then those rules will help us get formulas for the derivatives and to apply those algorithms in order to figure out what the function of this would be, what f prime of x would be. In this case for 35, since you're still in chapter 3.1, they haven't shown you how to develop those rules yet, and so they still want you to just use the limit definition in order to answer these questions. So we're going to go ahead and do that. So we're going to plug in 4x squared plus 2x here, and we're going to subtract it. Of course, we'll make sure, as Amo noted, to put our limit as x approaches a here. We're going to plug in a equals negative 2 to this guy. We're going to get 4 times negative 2 squared, 2 times negative 2. So that's going to be 4 times 4. And then this is going to be minus 4. That's going to be 16 minus 4, which is 12. And so we're going to get 12 for f of a. And a is negative 2. So down here we're going to get x minus negative 2. And now we're just going to start simplifying. So the first thing I'm going to note is that I believe I can take out a 2. I get 2x squared plus x minus 6. And then down here I get x plus 2. And then I'm going to check and see if this guy can be factored. So 12 is 1 and 12, 2 and 6. And then 3 and 4. 3 and 4 do give me 1. They give me 1 with a negative 3 and a positive 4. So leaving my 2 out, I'm going to do, and I'm going to sketch the rudimentary forms in here, x minus 3, x plus 4. But then we have to divide the a. So this will be 2x minus 3, and that one simplifies to x plus 2. Let me check it. That will be 2x squared, and then we get 4x minus 3x, which is 1x, and negative 3 times 2, which is negative 6. So that looks good to go. And then we'll drop down the x plus 2. The x plus 2's cancel out. And so now, and then of course I should all along here, this should say, instead of a, should say negative 2. Okay. But now that those canceled out, I'm going to just write it again, try to write it a little bit bigger for you guys. Now we're left with 2 times 2x minus 3. And now I can plug in that value of negative 2, and I get, let's see here, negative 4 minus 3, which is negative 7. Negative 7 times 2, which is negative 14. So check your work on your limits here. I'll zoom in a little bit. I should have done that maybe earlier. Just slowly go through it. Again, f of x, that's this. F of a, we plug in the a value to that. We get what it is. We plug it here. We take our a value, put it down there. I factored out a greatest common factor of 2. This is a GCF, greatest common factor of 2, that we pulled out of this entire thing. I then factored that thing by using the same method I've shown you. I got the sums that equal the b, but then I divided the a back out because I had multiplied it in to get the sum. Canceled those out. Came back over here. I now no longer have an undefined equation, so I can go ahead and substitute it in, and I get negative 14. Okay, what is that, and what part of the answer is that? F prime of negative 2 equals negative 14. That's just what we determined. So pause there, make sure you understand all of that, and go back and review the work, and hopefully you're good. So bear in mind this is an x squared function, and this x squared function, 4x squared plus 2x, has a plot. It's some type of positive parabola, and it's going to have a slope at a equals negative 2. Here we'll do a quick negative b over 2a analysis just to get a general sense of what's going on. So negative 2 over 2 times 4 means that the axis of symmetry for the upward facing parabola will be at negative 2/8, which is negative 1/4. And so at negative 1/4 is where this will be. So at negative 2, we know we're going to be on this side. We know that this is at negative 1/4. That's the x value. And so we know we're going to have a tangent here at negative 2 that's pretty steep, and is going to be something like that. And that's what we're finding. We're finding now the equation to this line. And what we found right here with this answer that's equal to negative 14 is that the slope of this line and the slope right there are equal to the same thing, which is negative 14. That's what you determined. They're equal to negative 14. That line's going to have a slope of that. So to do that, we're going to use our good old-fashioned friend here, point slope form. And we're just going to plug in our parts. So we know that negative 14 has to be what goes here. We just said that a few times. That's our slope. And now the point that they wanted us to evaluate it at was negative 2. And then we already plugged in negative 2 down here in order to get f of negative 2 here, which was 12. So we know that that's going to equal 12 here. And now we just rewrite this thing. And that's our equation. And that kind of makes intuitive sense, because if this is really steep and this is the axis of symmetry, that means that x equals 0 is over here, and this is going to hit negative 16. So yeah, way down here at negative 16, that line will cross through. And so anyways, they didn't ask us to do this. I'm just explaining to you what we just found. So you would want to do part B and have this work shown, and then you'd want to have part A, which would be the limit evaluation, of course completing it and showing the final step and concluding with that. And you need all that work shown. You don't need a sketch in this case, so don't fear about doing a sketch, but we're going to go ahead and put both of those equations into Wolfram Alpha as well, and give you a sense of what those look like. So give me 1 second. And get the paper where I have both. All right, so let's go ahead and pull that up. So we'll turn these guys off and we'll put in the first one, which is the original function 4x squared. And then we have 2x, and then we're going to have negative 14x and minus 16. And you can see there that that's that low y-intercept I was telling you about. that were to the left of 0, so we knew and predicted, even though they didn't require us, that it would be some kind of tangent on that side of the parabola. And again, that's both the slope of the tangent line and the slope at that particular instant on x on that original function. All right, our next problem is 43, which we're going to try to put this all into one big video and hope that nothing failed. So I'm going to put 43 under the document cam here and stall for a little longer. And let me readjust this now. There we go. Move things up. Leave that there for a little bit. Hope everybody's doing well. And I'm not going to talk about the derivatives in today's video. This actually has taken a good long time to get here. It's 11 o'clock at night. Surprised it took so long to get these done, but it takes time and I need to upload them. I also want to make sure they're on YouTube as a backup so that there's no problems with the server or anything like that that prohibits anybody from being able to watch them. So at any rate, I will make sure to give you some information on the derivative packet, and you won't be left hanging there, but let's make sure that we actually do kind of want to wait for that to be like in the end of video 2 and the start of video 3, because you kind of need to learn this stuff anyways. But don't worry, that's coming up soon. So I think we're in good shape. I'm going to pause the video there, and you guys start 43 on your own and get as far as you can. All right, so let's do it. So the book is a little bit sloppy on when to use the kind of the parent form and when not to. They even call the alternate form their main form, so most books don't do that. Let me just tell you that when you have these, which are 1 over x parents, they're much easier to solve with f of x plus h minus f of x over x plus h minus x. I always write it like this to emphasize that it's still the slope equation. Of course, x minus x is 0, and you could just leave those off. I like to write it like that. For me, it helps. So we're going to go ahead and use this one. Of course, the limit as h approaches 0. So let's do that. So limit as h approaches 0. And what did they ask for here? Let's make sure we don't lose sight of that. They asked for the derivative of the following functions at the given point. So actually, I should revise what I said. We have to use this equation because the other equation, okay, this one, I take back what I said a little bit. This is for evaluating at a point x equals a. This one, like I told you earlier, which you can also use this one for the ones that we use this one for. That's where it's like a Venn diagram where this is like a limited case with inside a larger case that this one does. This one does both, but this one only does one thing. This is a one-trick pony. It's only for evaluating at a specific point. This one gives you the function f prime of x. This one's huge. This is the one we use to develop all of our functions. But we can also use it to assess functions at a particular point. So let's go ahead and leverage this one right now. So now that you know which one we're leveraging, go ahead and pause the video and try to get as far as you can on that. All right, and I don't want to overwhelm you, so we're going to go one step at a time. So the first thing you should have is you should have that. Anywhere you had the t, you put in an x plus h. And again, these x's will just add out, but you'll notice that I have the convention of always writing it like this at the beginning. Down here, they simplify, of course, just to h. And now, you could have plugged it in here too. I like to plug it in second. So we're going to plug in, we want to leverage the general form, which will give us actual functions. But in this case, the reason we're using this form is it's just easier for 1 over x parents, and that's just something I know from experience. You can play around with doing it both ways and making your own choices on what's easier and what you prefer. Doesn't matter. You can do this one the other way if you want. Just take some more steps. I believe. I'm pretty sure you can. There's some that are impossible the one way and only possible the other way. And that's a fun thing to investigate. But at any rate, let's not lose the forest for the trees or whatever the saying is. So now we're going to leverage the form that gives us the generic functions at a specific point 1. So we plug in the point 1 here. We get 1 plus 1, which is 2, so h plus 2. I don't know why I have a 2 there. Let me pause and check. And the reason, of course, is because I had a typo. Of course, this is x plus 1, and here we put in x plus h. And this is the original, which is just 1 over t plus 1. But we use x instead, so it's 1 over x plus 1. So we put in 1, we get 2. Okay, so now that we have that, we're just gonna, what I'm gonna do is put the 1 over h over here in the front, and then I'm gonna do this divided by that, which is the same as all of this times 1 over h. So I'm just gonna put that h here, and then I'm gonna do all of this over here in scratch paper land. So that means I need to multiply both of these denominators by each other. So I'm gonna have 2 over 2 times h plus 2 minus h plus 2 over 2 times h plus 2. So let's write that out now nicely. So 2 minus h plus 2 all over 2 times h plus 2. And this is just heavy-duty algebra 1, adding and subtracting polynomial expressions with different denominators. And so we get that, and of course this will be negative h, this will be negative 2, 2 minus 2 will add out, and now we have 1 over h times negative h in the numerator, and then 2 times h plus 2 down here, and the limit as h approaches 0. Don't worry, I see that it's not able to be seen, so I'm going to scroll it up. So now we have that in our algebra. Now that h cancels with that h, giving us the limit as h approaches 0 of negative 1 over 2, and I'll just distribute that in. Pardon me, big throat clear there. Long trip down to Albuquerque today. We have 2h plus 4, and now we can plug in 0 and we get negative 1/4. What's negative 1/4? Again, don't lose sight of what we're doing here. The limit of the difference quotient takes the secant, collapse the little increment of difference that we have on whatever the function may be. So if we have something that's approximating the slope there, if we take this distance a and we collapse it to 0, we have the slope right there at that instant instead of the slope that approximates it. So this gave us the slope right at 1 of the 1 over x plus 1 function. So we're done. They just said evaluate the derivative of the following functions at the given point. We've done that, but let's go ahead and take a look at the graph to just get a little bit better idea of what we're doing. Okay, and what we can see is that 1 over 1 plus x has a vertical asymptote at negative 1, but it's otherwise very much like the 1 over 1 plus x function. And what we just found is that the slope at the point 1 is negative 1/4. So here's the point 1. And that looks to be about correct. Negative 1/4 slope seems to be that slope there. Now, this isn't going to be the tangent line, but we can put in negative 1/4 times x. And you can see that at 1, right there, that tilt is exactly the tilt that we have here. Now, we could do the same methods we did on the earlier problems to figure out exactly what the tangent line would be, like how do we shift this up to where it hits right at 1 here and touches right there. But you can get a rough idea by putting in the parent function, not the exact tangent. So hopefully that helps, and we're going to go ahead and stop there. That should give you an idea of what to do in Chapter 3.1. I want to remind all of you that what I'd really like you to do is pause the video now and send me a list of the hardest Chapter 2 questions. Now, if you did your work late, you're just going to need to wait till I get back and grade it next week, and it's just how it goes. It's not a big deal. We had a few students that were in that predicament. Each of you have individual arrangements based on your needs. So you may not have feedback yet. That's okay. You know if you didn't know what to do on a problem. So don't send me every freaking problem in Chapter 2, guys. You know, that's silly. But those of you that did your work on time and got your feedback and got some wrong, send me some clarifying questions to do on Chapter 2. Those of you that didn't get that far yet, do it on your own, and whichever ones you know are the trickiest of the tricky, send me a list of those that you know that you're going to need some extra time and practice on, and we'll go from there. And then again, as I mentioned earlier, the derivative worksheet or project or investigation that I've made for you. And I actually refined this one a bit, so I think it's a lot better now that I put some edits on it. This will be in the next video. I'm not going to put it in tonight's because, well, first of all, I'm exhausted, and second of all, upon reflection, you actually do need to mull over some of these concepts from this video first, and then you'll be prepared for it, because it kind of builds off some of the concepts, notably the concepts in the very first part in video we made today. So hope you all are well, and we'll talk to you on the next one, because we got 3 of these this week. So you guys hang in there, and we'll be back on synchronous Zoom next week. And I just hope everybody's well and that you're doing great. Talk to you later. Bye.